The next topic is principal components analysis. Principal component analysis takes in numerical variables, so you have to have only numerical variables. Then it converts them into set of numerical variables that have some nice properties. Okay, so and then so if you have 10 numerical predictors, when you run the principal component analysis, it will create 10 principal components. Okay, so 10 for 10. So if you're going to have 10 for 10, why bother? If you start with 10 variables and you end up with 10 variables, then what is the benefit? Now, well, the idea is when you take 10 variables of the original value and convert them into principal components, it's very likely that just a few of the principal components, maybe out of the 10, maybe we can use 2 or 3 and they will capture all the predictive power of the original 10 variables. So they remove the overlapping information because those variables may have overlapping information. So we're going to remove all the overlapping information and just uh, filter out the essence of what's in there in just a few principal components. And the final product is smaller. So even though you do get 10 principal components, you don't have to use all 10 of them. You can use probably 2 or 3 of them. Now, of course, you may not get all the 100% predictive power in the original variables in the principal, if you use only 2 or 3. But what if we get 99.9% of the predictive power in just 2 or 3 principal components? And when you leave out, say, 7 or 8 principal components, you're leaving out only less than 1% of the predictive power. So that's a good deal. So that is the underlying idea behind principal components. Okay, let's see how it is done. How does PCA do this? So it creates new variables that are linear combinations of the original variables. So linear combination seems kind of, it's nothing but weighted average of the original value. So you have, say, 10 columns. You multiply each column with a weight and add them up. Okay, so you use different weights. So you use one set of weights for the first principal component, another set of weights for the second principal component, another set of weights for the third principal component, and so on. So you come up with, if you have 10 variables to start with, you get 10 set of weights. So first set of weights will give you the first principal component, and second the second, and so on. And these new variables are called principal components, each of which is a weighted average of all the other variables. Okay? And when you do that, when you do that in a particular way, then you capture the information within the first few principal components. So this is the example we're going to look at: breakfast cereal. Okay, and it has all of these different variables in them. This is a description of each variable. So what we're going to do is we're going to take just 2 variables and run the principal component analysis to understand the concepts. And then we will run the principal component analysis for all the variables. Okay. So first, we're going to look at just these 2 variables: calories and rating. So here, okay, remember, so there are so many of them. So here is the calories variable, and then here is the ratings variable. Okay, so these are the 2 that we're going to look at. And to understand what the PCA does is, okay, if you prepare a covariance matrix, okay, so here is the covariance matrix, right? And the correlation between these 2 variables is negative 0.6869. Okay, so the total variance, okay, so this is the total variance, this is the covariance. Okay, covariance is a measure of common variance. So that is the shared information, the overlap. Larger, either negative or positive side, larger covariance would result in larger both positive and negative side correlation, and that means there is a lot of sharing or a lot of overlap in the information, okay, which is not keeping both of them is not going to be helpful to that extent. Okay, so if you look at the variance, okay, we can prepare this covariance matrix. Okay, so let's look at it in Excel. Okay, so here is the data, original data, and here is our two variables that we have selected, right? So calories, rating, and then we have variance of x sub 1, variance of x sub 2. So this is x sub 1, this is x sub 2. Okay. So we can prepare a covariance matrix like this. So if you have var.s function, okay, so we have calories. So that gives you the variance of calories. Now the var.s of rating, so that gives you the variance of rating. Now you can do covariance dot s, okay, of the first array calories, and then the second array rating. Okay, so that gives you the covariance. Okay, so covariance of x sub 1 with x sub 2 is same as x sub 2 with x sub 1. So the diagonal will be the same. Okay. All right. So variance of x sub 1, okay, variance of x sub 1, variance of x sub 2, right? Now if you take the sum of the two variances, so that gives you the total variance between the two variables, and then you can express each variance as a proportion of the total. Then you say what percentage of the total variance comes from x sub 1, what percentage of variance comes from x sub 2. Okay, so that's what we had here in the PowerPoint. Okay, 66 and 34%. So now what we will do is we're going to run a principal component analysis, which is going to come up with linear combinations, and we will call this Z1 as the first one. So in 2-dimension, linear combination is a straight line. So it's coefficient times calories, so A times calories plus B times rating. So for each value you multiply A times calories plus B times rating, and you get a line, a point on the line, okay, for a given A and given B. Then you have a different weight that gives you Z sub 2. So you come up with these weights in such a way that the weights, when you compute the Z sub 1 and Z sub 2, they will line up exactly opposite, like perpendicular. So one line is, this is the term used is orthogonal. So Z sub 2 and Z sub 1 are orthogonal to each other. So that means they will be completely uncorrelated. So the correlation between Z1 and Z2 will be 0. Then we can look at what is the variance of Z1 and what is the variance of Z2, and that would be the total power that we have, predictive power we have between Z1 and Z2. So how do we compute Z1 and Z2? So that's in R we have a package for computing PC. I think it comes from within the base itself. So let's go ahead to R. Let's head on over to R, and let's go ahead and compute the Z sub 1 and Z sub 2, and then come back and discuss some more.